Hello, guys. So today I'm going to do the May-June 2025 variant 22 paper. I'm also going to do the variant 23 paper. And the reason why I'm doing these papers specifically is because I do think that your October-November papers are going to look exactly the same or kind of similar to what you see now for the May-June papers. Because it appears that Cambridge has once again sort of changed the structure that they set their papers in. So the style of the paper. And this, I believe this is going to be the exact style for your paper. So it's better that we prepare very well for these papers. So if you do these papers, paper one, I've already done the video. Please make sure you watch it. I know these videos, I know they can be boring, but yeah, your grades will be boring too if you don't watch these videos. So I encourage you to watch the videos. I'm spending my time here doing this for you guys. All right, anyways, let's do this paper quickly. Let's see if we can get 1 or 2, 3 things that I can help you with. Okay, so question one. Question one says diamond and graphite are both crystalline solids made from carbon atoms. So they still maintain their style of examination where they give you a statement and then they ask questions. You must read these questions. You must read the command words. If there are 2 command words in a question, make sure you answer to both command words. You respond to both command words. Otherwise, you won't get the marks. Be careful of 1-mark questions demanding 2 things, because then on the marking scheme, they will say they want this and that. And if you don't satisfy both points, then you end up losing a mark. So again, notice how I approach the paper. Try to approach it in a similar way. Even if we don't get 100%, but I'm sure we'll get 100%. If we don't get 100%, we will get 98%, which is very good. So let's see if you can get 98%. All right, diamond and graphite are both crystalline solids made from carbon atoms. Okay, so they are allotropes of carbon. Graphite conducts electricity. Diamond does not conduct electricity. Name the type of lattice structure present in these crystalline solids of diamond and graphite. So obviously we know these are giant molecular lattices. So these are giant molecular structures. Okay, so giant molecular structures. Giant molecular, because they said structure. If they had said structure and bonding, then we say giant molecular structure with covalent bonding or giant covalent bonding. Okay, so this is giant molecular structure. Okay, that's the structure present in both of them. Explain how graphite conducts electricity. It conducts electricity because they say how. You see, they say explain what? How graphite conducts electricity. Then we say the delocalized electrons, the delocalized or mobile electrons, the delocalized electrons carry electrical charge along the layers of graphite or within the layers. Explain why diamond does not conduct electricity. Because it has no mobile ions or electrons to carry electrical charge. Okay. Separate samples of phosphorus 5 chloride, that's phosphorus pentachloride, and silicon 4 chloride are each added to an excess of cold water. Write an equation for each reaction. Phosphorus pentachloride is this one, the one of those that do not obey the octet rule. This one here reacts with water. They didn't say that they want me to include state symbols. I'm not going to include them, but you can include the state symbols. So here you form what? Phosphoric acid, isn't it? Phosphoric acid. And what happens to the chlorine? You form hydrogen chloride gas. So you see misty fumes of hydrogen chloride. We need to balance the chlorines. There are 5 that side, so I'll put a 5 here. Then in terms of hydrogens, I now have this 5 plus this 3, that's 8. So I need to put a 4 right here. Then I also have 8, 4 oxygens balanced. Silicon tetrachloride, that's Si Cl4 reacting with water, and this forms silicon dioxide, which is a covalent compound. Plus, of course, where is the chlorine? Hydrogen chloride gas. Balancing the equation, I need a 4 to balance the chlorines. Now I have 4 hydrogens here, so I must put a 2 here. Oxygens have also balanced. Describe the appearance of phosphorus 5 chloride. Phosphorus pentachloride is a white solid. We know that one. White solid. And silicon 4 chloride, not oxide. Oxide is the same, right? Silicon oxide. You are used to silicon oxide because it looks like diamond, isn't it? But this is the chloride. At room temperature, it's a liquid. So this one will be a colorless liquid because silicon is not a transition metal. So we don't expect any beautiful colors here. It's colorless liquid. Okay. Compare the appearance of the mixtures produced when each reaction is complete. On completion, the first reaction. So how can I answer this? Then I can say with reaction with PCl5 produces a colorless solution, isn't it? Phosphoric acid produces a colorless solution. Colorless solution. The appearance, we are focusing on the appearance. Talk about things you can see. Colorless solution. Okay. Reaction with silicon tetrachloride. Silicon oxide is a solid, so this one you produce what? A white precipitate, or yeah, you can produce a white precipitate because I'm mixing water. Water is a solvent that is a liquid, and then the silicon tetrachloride is also a liquid. So bring 2 liquids and the solid appears inside, so I can say white precipitate here. So white precipitate, that's what I'll say. Some oxides are amphoteric. Describe what is meant by amphoteric. Amphoteric means a substance. This refers to a substance that behaves as both. We know this one. It behaves as, oh, my pen. What's going on with my pen here? Behaves as both an acid and a base. You could say or base. Identify the formula of a period 3 oxide that is amphoteric. Everyone knows aluminium 3 oxide. Okay, there it is. Okay, amphoteric from period 3. Remember, water is also amphoteric, but it's not from period 3. The melting points of different oxides are shown in this table. There, and then melting point oxide, force of attraction broken during melting. Sulfur dioxide is a gas, so simple molecular forces of attraction between are intermolecular forces. Water, we have hydrogen bonding in water, silicon 4 oxide covalent, then we have ionic compounds. Okay, so what they want, they say complete table 1.1 by identifying the strongest force of attraction in each oxide that is broken during melting. Use the abbreviations below. Okay, I see. So sulfur dioxide is like this. Remember, oxygen forms 2 bonds, so we do this, we do that. Sulfur, okay. I don't know. Check to see if there is. This is not carbon, so there might be lone pairs here. But anyways, that's not the point. The point is, if I have this one, then there's polarity here. Sulfur oxygen is more electronegative, so it will be delta negative. This will be delta positive, right? So then these polarities are permanent. So between sulfur molecules, if there's another molecule of sulfur like this one, like so, the attraction between the sulfur molecules is this one here. You see this one? That's a permanent dipole attraction. So here we have permanent dipole attraction. And then in water, as we all know, water forms hydrogen bonding. We get that network of hydrogen bonds that forms tetrahedral arrangement that allows ice to then push the water molecules into a tetrahedral conformation, creating air pockets in between and making ice less denser than water. Remember, hydrogen bonding is formed when you have oxygen, nitrogen, or fluorine bonded to hydrogen, and there's a lone pair. So water is like this with two lone pairs of electrons here. So then you can form a hydrogen bond here, okay? Because we have a lone pair on oxygen and a hydrogen. So this one is hydrogen bonding. So I'll write H. Silicon chloride is like diamond. So in diamond or in silicon 4 oxide, it's a network of tetrahedrally arranged atoms. So each silicon atom is surrounded by four oxygen atoms covalently bonded. So your covalent bonds are the force of attraction inside. They are the intermolecular force, if you will, but it's not a force, it's a bond. So these ones, you have covalent bonds, very high melting points. So here there's covalent bond. But in sodium oxide, that's metal to nanometal, the bond, positive ion and negative ion, come together. Then you have an electrovalent bond, which is an ionic bond. That's what you break. Ionic crystal, similar to magnesium oxide ionic crystal. So we do that. Move on. A student suggested the following hypothesis: the stronger the covalent bond between atoms in nanometal oxides, let's underline this one, it's important. Only the nanometal oxides we care about here, the higher the melting point. The hypothesis is that the stronger the covalent bond between atoms, remember, not molecules, but between atoms, in covalent and nanometallic oxides, the higher the melting point. Use table 1.1 to deduce if this hypothesis is true or false, or if there is not enough information to make a conclusion. Explain your answer. This is similar to the question I saw in variant 2.1. So like I said, I do think that your October-November papers are going to have a similar structure. So please go through these papers, make sure that you thoroughly understand this structure of your chemistry paper. Right, so let's go back. Let's look at what tested this hypothesis. Let's go and test it. We are focusing only on non-metallic oxides. So this one and that one, and this one also. These are oxides, the ionic ones are metallic oxides. So let's look at this. If you look at silicon 4 oxide, this one, we are breaking covalent bonds between atoms. So we break the bonds, the covalent bond between silicon to oxygen and so forth. So yes, we have covalent bond. We need a lot of energy to break the covalent bond. So we expect high boiling point. But we need to compare it to something else so that we can make a conclusion to test the hypothesis if it's true. So if we consider water here, we are not breaking the O to H bond. We do not have the bond energy of the O to H bond. That's not what we are breaking. It's not a process by which we break those covalent bonds, those sigma bonds there. We are breaking intermolecular forces between the molecules, which is the hydrogen bond. And similarly, in sulfur dioxide, we are breaking the intermolecular forces, not the sulfur to oxygen double bonds. No, that's not what we are breaking. So just the information from sulfur, from silicon silicon 4 oxide, that alone is not enough because we need something else to compare and see if that is the trend. So I can say here that there is not enough information. There is not enough information. Enough information. I'll say in H2O and sulfur dioxide, covalent bonds are not broken. Covalent bonds are not broken during melting. Only the intermolecular forces are broken. Okay, so there's not enough space for you to go and talk about, oh, silicon 4 oxide is the only one that is, so we're not going to tell that whole story. I think this answer is sufficient. Question 2, a sample of iron contains 3 different isotopes. So iron has 3 isotopes and has a relative atomic mass of 55.8. This information, they cannot tell us this information for nothing. So please keep that in mind. Define relative atomic mass. Relative atomic mass, we know how to define relative atomic mass. We know how to calculate it, therefore, from mass spec data. So we know how to answer this question. Why? Because we know, first we have to take the abundances. So we can say it is the weighted, because we take into account the abundance, the weighted what? The weighted average, because we calculate an average. But average of what? The weighted average of the masses. Okay. This starting sentence, this part of the sentence, students always mess this one up, because it is not the weighted average mass. It is the weighted average of the masses, not the weighted average mass. Don't say that. I don't like that. Say it is the weighted average of the masses of all the isotopes, of all the isotopes. Of an element, right? 1 mark, relative to, or in comparison to, relative to a 12th of the mass of a carbon-12 isotope. You could say compared to the mass of the unified atomic mass unit, or relative to the unified atomic mass unit. Table 2.1 shows the abundance of 2 of the isotopes of present in the sample of iron. Remember, the sample of iron has 3 isotopes. Here they give us information about 2, okay? Use table 2.1 to calculate the relative isotopic mass of the third isotope. So in other words, we need to calculate the relative, okay, you can see the relative isotopic mass is isotopic, how would I say isotopic? Isotopic masses of these 2 are given, but we need a third one. So there's another ion here of some mass, X here. Okay, we don't know the mass here. And that mass is more correctly given to the 1 decimal place, is X here. And what is the abundance of that? So we can calculate, I can see this must add up, we see the percent, the abundance is a percentage. So it must total 100%, isn't it? So we are going to say 100 minus 91.9 minus 6. What do we get? We get 2.1. So the percentage abundance of the other isotope is 2.1. So relative atomic mass, we can calculate it. We have all the information. If you go back, remember they gave us the relative atomic mass of iron. It's 55.8. Then you come down here. You say 55.8 is equal to, then you take the mass here, which is 53.9. Please do not use 54, use 53.9. Multiply that by the 6.0, but I'm just going to write 6. And then you say plus 55.9, right, times 91.9. And then you say plus 2.1x. Okay, like that. And then all this divided by 100. To save space, I'm going to linearize my problem and just multiply by 100 this side. You understand? Okay, then I have 5580 minus whatever these first two brackets are, which I can quickly calculate. Let me punch that in my calculator. That would be 53. Okay, sorry. My calculator is on screen, gives problems. So that's 53.9 times 6. And then plus 55.9 times 91.9. And then that gives me 5,460.61. 5,460.61 equal to 2x. 2.1x, it's 2.1x. Okay, so now guys, please just solve for x here. So I'm going to say minus 5580 gives me that, divided by 2.1 gives me 56.85. Okay, so this implies that x equal to 56.85. This to 1 decimal place. You can see the others are given to 1 decimal place there. In other words, 3 6. So here you say 56.9. Okay, deduce the number of pairs of electrons in the 3D subshell in an iron 2 ion. Okay, all right. Ion is after argon core, so we do argon, and then we say 3D, and then 4s. Right, this is iron 2 ion. So here it's 0, because 2 electrons have been lost. So ion is number 26, so 3d6, like that. So how many pairs of electrons are in the 3d orbital. Remember Handy's rule, you put electrons singly first, right? We want to put 6, so now I have 5, then I put the 6th one. So there's only one pair, okay? So I'm gonna say this is one pair. There's only one pair in it. Okay, good. They say sketch the shape of the lowest energy orbital in the shell with principal quantum number 2. Okay, principal quantum level number 2, that's we have 1s, 2s, 2p, and so forth. The lowest energy in quantum 2 is the s orbital, which is spherical. So just draw that. Easy. All right, complete table 2.2 to show information about particles in one ion of ion 3+ ion. This is ion 3+. Ion is number 26 on the periodic table. That means it's got 26 protons, 26 electrons if it's an atom. But this one has lost 3 electrons out of the 26, so it's got 23 electrons left. Here, what is it? The subatomic particles? Which one is 30 in this? Remember, ion is number 26. 56 minus 26 is 30. But 56 is the nucleon number, which is the number of protons plus neutrons. So that means 30 is the number of neutrons, because 56 will be 30 plus 26. 26 is the number of protons. This one is the number of neutrons. And this one is the nucleon number. Okay. The atomic radius of iron is 1.26 times 10 to the minus 10 meters. So just the change to the radius, if any, after an ion atom reacts to produce ion 3+ ion. Explain your answer. Okay, so you have iron atom. It will have 26 protons, 26 electrons. Then you have the same guy, so still 26 protons, but less electrons. This one is 26 electrons. This one is 23 electrons. Okay, so let's think about the configuration. Remember, I did this before, but I will do it again. So argon will be like this, and then you have 3d, 6, and 4s0. That's in Fe3+. In Fe atom, you have 4s2. So in Fe3+, you have lost these 2 electrons from the 4s. So there's 0 here. Oh, no, yeah, you actually lose another one here. So this is like this, 5. You understand? So in Fe3+, you have lost 2 electrons from here and 1 here. So you're left with 6. There you have lost. So this shell is completely gone. So that now we have less shielding effect because we have less shells. So we can say that the radius decreases. Suggest the change to the radius, if any, of the ion. Okay, the radius decreases or gets smaller. Okay, should I say decreases? I don't like that. I don't like gets smaller. The radius gets smaller. Okay, why? I would say both Fe, which is the atom, and Fe3+. You have the same nuclear charge, but Fe3+ is lost the 4s shell. Hence, outer shell electrons, outermost electrons, or valence electrons, are strongly attracted to the nucleus. You could say as there is less shielding effect. Okay, let me just say that as there is less shielding effect. It's kind of like the same reason for ionization, but we're not talking about that really. But yeah, maybe we said too much, but that's it. Okay, question 3. C3H6, that's a general formula. Cn, the number of hydrogens are double those of carbon, so it's an alkene. Reacts with hydrogen bromide in an addition reaction. Yes, it's an alkene because it undergoes addition reaction. Define addition reaction. This is a reaction in which what? Two or more, I'll say, two or more reactant molecules or reactants react to form one product. Isn't it, guys? That. Okay, I don't like how I wrote product there, but you know what I'm talking about because you can hear me. Okay, complete figure 3.1 to show the mechanism for the addition reaction between, that's one, propene and hydrogen bromide to produce 2.3 no, where am I getting 2.3? 2 bromopropane, include charges, dipoles, lone pairs of electrons, and Kelly arrows as appropriate. They always ask these mechanisms of reactions. Always start with your dipoles, always. So we can see hydrogen bromide, there is a permanent dipole here that exists. Always start with this to make sure that you don't forget the dipoles. Kelly arrows always start where the electrons are to where they are needed to a positive charge. So from where the electrons are to a positive charge. So electrons are in the bond. They will attack the positive hydrogen like that, repelling the electrons in the bond, giving them to the bromine completely. Please don't start your Kelly arrow there from the hydrogen. The electrons are in the bond. Then you draw that Kelly arrow to the bromine. Now, here you need to think about Markovnikov's rule, isn't it? Because hydrogen must always go to where there are more hydrogens. The effect of that is that if you put hydrogen first to where there are more hydrogens, then you are forced to put a plus on the side, the carbon that has less hydrogens. That gives you a stable intermediate. Okay, so this one, I'll draw it like what? I'll just draw what I'm seeing there. CH3C, and then like that, and then C, and then this is the hydrogen you added. These are the ones that were present before you added your one. And this side, there was a hydrogen that was there, and then this then becomes positive. You see, like that. So this is what you get. And then the bromine that came from there then becomes bromide nucleophile like this. And then electrons are here. Those ones will attack the carbon there, like that. So I'm done with this mechanism. How many marks? 4. For what? I think 1 for charges. Second one for Kelly arrows that are correct on the first step. And then correct intermediate. And then lone pair on bromide. 4 marks. That's fair. Explain why the major product of this reaction is 2 bromopropane rather than, I already said it, that's what we're talking about, Markovnikov. So let's talk about this. So we can say 2 bromopropane is formed via a stable secondary carbocation. Right? Okay, you can say, if you want, you can say stabilized by the positive inductive effect, by the positive inductive effect of electron donating alkyl groups. You can go ahead and say that 1 bromopropane is formed via a primary carbocation. which is unstable, or via an unstable primary carbocation. You can say that. All right, hydrogen gas and nickel are added to alkene X. Figure 3.2 shows how concentration of X changes with time. So we can see that X is the reactant, so it's the concentration of it is going down, it's being depleted over time. So use figure 3.2 to identify the limiting reagent in this reaction. Explain your answer. So two things, identify the limiting reagent, and then explain your answer. So two things for 1 mark. So be careful of these kind of questions. Right. So limiting reactant is, of course, our X, isn't it? No, it's not X. It's hydrogen. Why do I say that? Because X was not all of it used. You see, the concentration didn't go down to 0.0. So the limiting reactant, we could say limiting reagent is hydrogen gas, because some amount of X remained. You see? Yeah, it remained at the end of the reaction. So you can see it remained constant there. It remained. Okay, so we could just say that and just full stop. I think that's fine enough. Use figure 3.2, which is the one above, to describe how the gradient changes as the reaction proceeds. State what, again, two things, 1 mark. State what this shows about the rate of reaction during this, during this reaction. Okay, so first of all, what's happening to the gradient? The gradient is steeper, shallower, zero here, okay? So the gradient is getting shallower and shallower, so the gradient is decreasing. Okay, so describe how the gradient changes. Gradient steadily decreases. Steadily decreases. Okay. State what this shows about the rate of reaction. The rate of reaction decreases. What am I saying? I wanted to say the rate. The rate of reaction decreases as the gradient decreases. As the gradient decreases. Kind of like they are directly proportional, right? Right, moving on. Hydrocarbon Y contains 2 double bonds, 2 C to C double bonds. There are no other functional groups present. Y reacts with an excess of hydrogen to produce hexane. Adding hydrogen to a double bond is hydrogenation. So you can add hydrogen to compound Y and you produce hexane. Let's draw hexane. Hexane is the 1, 2, 3, 4, 5, 6, isn't it? 1, 2, 3, 4, 5, 6. Okay, good. So this is produced by adding hydrogen to a compound. Obviously, that compound would have been like this because hydrogen does not add carbons. So that means I had 2 double bonds. You can place them any way you want, but there it is. Now, each double bond requires 2 hydrogen atoms. So then I must put 2 here, because each double bond carbon will require 2 hydrogen atoms. So you need 4 hydrogen atoms. All right, we're good. Now they say use table 3.1 to calculate the enthalpy change per mole of this reaction. Enthalpy change per mole of this produced in this reaction. That's easy. So I can just look at the total number of bonds. So this side I have 1, 2, 3, 4, 5. So I have 5 C to C bonds. Okay, let me save space here because of what I will need to write. I'll say I have 5 C to C bonds. And then I have how many hydrogens? 14. So that means I will have 14 C to H bonds, right? Done with that part. And then here, of course, I have 4 hydrogen bonds. I'm just going to add them at once. Let's see how many C to C double bonds. C to C double bonds, I have 2 of them. And remember, my total carbon-carbon bonds are 5 from that side. So these ones will be 3, but you can count 1, 2, 3. So 3 C to C single bonds. And then how many C to H? It's an alkene, double alkene. So how many hydrogens? if you will, you can count. There are 2 here, hydrogens. There's 1 here. There's obviously 1 here. There's 1 there. There is 2 here. There is 3 here. So how many are there? 10, you see? There are 10 C2H bonds. Okay. And then, of course, I have 2 H2H bonds because I have 2 of these molecules. Right. So now that I have this, my life is easy. All I need to do is put the energies. So let's start with the energies here. So this is going to be, wait, what is the energy for this one? 610. So 2 times 610. Okay, put that in brackets. And then I have 3 by 350. What am I writing once again? 3 by 350. Okay, and here I have 10 by what? What is the C2H bond here? 410. So that becomes 4,100. I'm going to multiply it for so long. H2H is 436. So you have 2 times 436. This is the total energy on the right-hand side. If you add all these numbers on the left-hand side, the bond breaking, so endothermic side. So the exothermic side, which is the bond formation, is going to be 5 multiplied by C to C is 350, right? And then 14 by 410. Okay, 14 by 410. Look, we could have ignored, notice that we have C to C bonds here, single bonds, and so forth. We could have cancelled those that are repeating. It's like, for instance, I could have cancelled this 10 here, and then cancel 10 here and be left with 4. But look, I'm not going to do that, just complicate my life. So I'll start with the total for the exothermic side, which is the bond formation. So total for that side is 5 times 350. Gives me whatever, I'll say, put that one. 14 times 410. And then I'll just get my total here. That gives me 7,490. So remember, this will have to be negative. This one is 7,490, but please immediately put a negative here because it's exothermic side. Then you go and add up the values for the other side. So the other side, you have 2 times 610. Okay, if you're good at mental maths, you can do mental maths, but I want to encourage you not to do it. Please use your calculator. You're allowed to use it. 350, close bracket, plus next one. What is it? 4,100. Okay, this one we've got. Just plug it in, plus open bracket again. 2 by what? 436. 436, close the bracket. And then I get 7242, 7242, like this. So then I must just subtract the 7490. So minus 7490, because then we kind of adding them. Then it's giving me negative 248. That would be my answer, negative 248. Okay, good. Right. Hydrocarbon Y reacts with hydrogen gas. Figure 3.3 shows the distribution of energies of hydrogen gas at temperature T. Area A represents, there's area A, represents the number of molecules with energy greater than or equal to the activation energy at this temperature T. Now, what do they want us to do? Annotate figure 3.3 to show the effect of adding nickel to Y and hydrogen gas at this temperature. So nickel is a catalyst for this reaction. It will lower the activation energy. So I'll just do this. So then say EA, then I can label. You can say EA cat for catalyzed, but I can also write here with nickel, without nickel. That's all good enough. Then they say area B, which is not labeled on figure 3.3, represents the number of molecules with greater energy than or greater than or equal to the activation energy when nickel is added. Okay, at this same temperature. So that means they're talking about this. That's what they didn't highlight. That would be B, this. Okay, what I've highlighted now. So because that's the energy of molecules with the catalyst, those with the energy greater than or equal to the activation energy. Command word number 1, state the difference, if any, between areas A and B. Okay, so area A, I can say area A, that one, is smaller than area B. Full stop. I've stated. And then they say, explain the significance of your answer on the rate of hydrogenation. Okay, that means, okay, area B, area, okay, I see. So a rate of hydrogenation is higher or faster, or faster. Let me say rate is higher. I don't like saying rate is faster because rate already includes per time. It's already a frequency. So this one I'll say is higher. Rate of hydrogenation is higher in the presence of nickel, okay, which is area B. I'm trying to find a way to shorten my words with nickel, okay? Let me say that. Then why? Because the proportion of molecules, we say this at IG, it's a very important answer at IG also. If you miss this statement, they penalize it. The proportion of molecules with energy equal to or greater than activation energy is higher. EA is higher. Hence, more, or I'm tired of using the word higher, but I'm going to say hence a higher frequency of collision. A higher frequency of collisions. Okay, kind of something like that, make it fit. Okay, alkene Z contains two C2C double bonds. Z reacts with an excess of hot concentrated acidified potassium manganate to produce these guys here. These are harsh oxidizing conditions. We have two double bonds, keep that in mind. So, okay, this one is easy, right? We are breaking, remember, this is the one where you break, the double bond is made of a sigma bond and a pi bond. You break both of them. So for me to get a ketone, which is this, it means that I had an R group on the side of the carbon of the double bond. And that would have been on penultimate or one end. So I would think that this would have looked like this. So kind of like this. And this one, you see, it's a dioic acid with 3 carbons. So this one would have been, okay, let me do it like this. And then I'll change and write it properly. CH3, C, CH3, C like the double bond. And this double bond would have been broken here, going onto a carbon that had a hydrogen, which is why now we have a carboxylic acid. Because when it was broken, it became an aldehyde. And then the aldehyde was then further oxidized to a carboxylic acid. So then we go to the CH2 that they have there in the middle of the dioic acid. And then obviously this side we repeat, we have a hydrogen, and then we have a double bond. My pen now. And then we have a double bond to what? A double bond. This is the second double bond. And then it was also broken. But we see carbon dioxide. That means here I had carbon that had 2 hydrogens, because when you have 2 hydrogens, will form carbon dioxide. So this is what it looked like. So if I was to draw this, I would draw it like so. How many hydrogens? Okay, how many, carbons. Okay, I'm on this carbon. 1, 2, 3, 4, 5, 6. I think 6, isn't it? 1, 2, 3, 4, 5, 6, like so, with a double bond here and a double bond here, like so. Yeah, and then this CH2 in the middle. So I've drawn it correctly. Okay, so this would have been the compound. Okay, like that. That's Z. Okay, question 4. Propanoic acid that reacts with the reducing agent Q to produce propane 1O. So it's reduced to an aldehyde. The aldehyde is further reduced again to a primary alcohol. Suggest the formula of the reducing agent. So we need a strong one. So I'm going to use lithium tetrahydroaluminate. This one here. Okay, complete the equation to show the reduction of propanoic acid to propane 1O and so forth. The structure of propane 1O is given, the molecular structure. There it is, CH2. That is the structure formula, isn't it? Like this. And then you can see here I had lots of oxygen. I had 2. Now I have 1. Where's the other oxygen? Put water there. Right. My oxygens are balanced, but let's look at the hydrogens. On the right side, you have 2 hydrogens plus 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 this side. In propanoic acid, I have 6. So I need 4. I need to add 4 hydrogens here. I need 4 so that I have 10, 10 on either side. Right, so that's it. It's balanced. Propane 1O is converted to compound T in a 3-step synthesis. Propane 1O, a primary alcohol. In step 1, it's reacted with thionyl chloride to produce compound E. So that means we produce, it's a substitution. The OH is replaced by chlorine, then you form a halogenoalkane. Compound E is a halogenoalkane. It's chloropropane, right? In step 2, that halogenoalkane reacts with a suitable reagent to produce butane nitriol. Important. Butane, propane, that means we added carbon. So, and it's nitriol, so we need to add cyanide. In step 3, butane nitriol is heated with this, okay? In the book, we know that nitriol compounds can be hydrolyzed with hydrochloric acid, dilute hydrochloric acid, to make a carboxylic acid. Now they are not talking about that acid hydrolysis. They are adding sodium hydroxide. Okay, let's get to the questions. Name the type of reaction that occurs in step 1. Step 1, chlorine replaces OH. It's substitution reaction. Substitution reaction. Identify the reagent and conditions required in step 2. Step 2, I already said we need to add nitriol. So I'm going to use ethanolic potassium cyanide, right? And then conditions, you need to hit this because you have a halogenoalkane. So ethanolic potassium cyanide, and then you hit that. Okay. Why ethanolic? We need to remove OH to put the chlorine. So if we use aqueous, then there's too many OH groups in the environment. You don't want that. So ethanolic. Construct an equation to describe the reaction of butane nitriol with that. Okay, we know that with dilute hydrochloric acid, we produce a carboxylic acid. It's acid hydrolysis. So in this case, they said what? Butane nitriol. Butane nitriol will be CH3, CH2, CH2, and then the nitriol group, like so. That's butane nitriol. Reaction with sodium hydroxide, so plus NaOH. So what you are going to do is you are going to change that to CH3, CH2, CH2, and then you break this triple bond between C to N, and then it becomes COO minus Na plus. And then what happens to the nitrogen that comes from there? It forms ammonia with the hydrogen. Okay, then you form ammonia. So that's what happens. Okay. It's kind of like you form sodium butanoate. That's sodium butanoate, if you will call it. Like it's kind of like an ester, but with a metal this side. So it's a salt. This is kind of the same stuff you find in soaps. Or think about something like a fatty acid. Do you have hydrophobic tail, hydrophilic head? That's what's going on there. Okay, let me erase these things here. Then we can continue. Right, name the type of reaction that occurs in step 3. Oh, we said it. We are breaking the C to N triple bond. So it's hydrolysis. But in alkaline, because sodium hydroxide is alkaline. So it's alkaline hydrolysis. Alkaline hydrolysis. Or hydrolysis, whatever you say. Okay. Then compound A, B, and C belong to the alcohol homologous series, so they are alcohols. Each molecule of A, B, and C contains 4 saturated carbon atoms. no double bonds. Identify the type of hybridization shown in the saturated carbon atoms of all alcohols. So imagine if you have something like this, and then I have OH here, the carbons are these ones, you see? The hybridization around each carbon, because there are 4 covalent bonds, remember there are 2 hydrogens here, there are 4 sigma bonds. Hybridization is sp to the power of sigma bonds minus 1. So you say sp to the power of number of sigma bonds minus 1. So it's sp, sigma bonds were 4, 4 minus 1 is 3. So it's sp3 hybridized. Okay. Identify the gas produced when sodium is added to the separate samples of each alcohol. You know, if you have ethanol, let's say, for example, ethanol. Ethanol is this guy, all right? When you add sodium metal to this, sodium replaces this hydrogen, and then you have minus and Na plus, like a salt. So this will call it sodium ethoxide. So they said what? And then what happened to the hydrogen that leaves? It is formed as hydrogen gas. So here the question says, identify the gas that is produced when sodium is added to an alcohol. It's hydrogen gas. Hydrogen gas. Describe the role of sodium when it reacts with alcohols. All right, so I said in the example that I just erased, I didn't know they were going to ask a question like that. So if you have sodium, remember, I had sodium metal. When it reacted and attached on the alcohol, the ethoxide that I removed, the sodium ethoxide, isn't it? I said it's going to be something like CH3, CH2, or minus Na plus. Can you see the oxidation state of sodium has gone from 0 to +1? So all sodium has been oxidized, which means sodium reduces the alcohol because itself is oxidized. So sodium metal is acting as a reducing agent because itself is oxidized. So it's a reducing agent. Okay. Easy. Right. Table 4.1 shows the results of 2 tests on separate samples of A, B, and C, those 3 alcohols. Alcohol A, when it reacted with the acidified potassium dichromate 6, under reflux, it remained orange. That means it could not be oxidized. If it was an alcohol, I can tell you it was a tertiary alcohol. No visible reaction again with the iodoform tests, the triiodomethane reaction. So this one is a tertiary alcohol because it could not be oxidized. So 4 hydrogens. I'll put an OH here. I need 4 carbons. Remember they said all these alcohols are 4 carbons. So I must put the other carbon here so that it becomes tertiary. So there is the tertiary alcohol. It cannot be oxidized because the carbon to which the OH is attached, this one, it has got no hydrogen to remove. Oxidation is the removal of hydrogen, but that carbon has no hydrogen, so it cannot be oxidized. Hence, we did not see anything. Even when we actually had to apply heat with acidified potassium dichromate, nothing. B and C, we saw a positive test for oxidation. So that means those were probably primary alcohol or secondary alcohol, right? B, no visible reaction with triiodomethane reaction or iodoform. So that means B could not have been this one. How many carbons? They said 4. 1, 2, 3, 4. It could not have been this one. Because if it was, it would have given a positive test here. Why? Because of this methyl. When I oxidize this, it will become a methyl ketone. So then I would have gotten a positive test. So B is not this one. So if it's not this one, and it gives a positive test for oxidation, then it's a primary alcohol. It's this guy, isn't it? Provide a possible name for B. It's butane 1-O. Butane 1-O. It's this one. You see? And then they say orange to green, pale yellow precipitate. Yes, it's an alcohol. It's got a methyl. That's butane 2-O, the one that I've left there. Butane 2-O. That one will give positive tests for both of these tests because it's got a methyl group, and also it's an alcohol that can be oxidized because there's a hydrogen on the carbon to which the OH is attached. Okay, we're done with that part. Question 5. The structure of vitamin C is shown in figure 5.1. Vitamin C, there is vitamin C. Deduce the empirical formula of vitamin C. Method of counting the carbons. I think I saw a similar question in 2.1, isn't it? 1, 2, 3, 4, 5, 6 carbons. How many hydrogens? Start with the hydrogens that you can see. Then you go to the ones you can see. So there are two hydrogens here. There's one here. There is one here. No hydrogen, no hydrogen, no hydrogen. Yeah, I think I'm right. So 4, 5, 6, 7, 8. So H8. Oxygens are always written. So we look for all the oxygens. 1, 2, 3, 4, 5, 6. So 6. They want empirical formula. Empirical formula is the simplest ratio of this. Divide everything by 2, then you get C3, H4, O3. That's it. Done. Okay. The mass of vitamin C present in 150 grams of lemon is found in an experiment. So you have a lemon, 150 grams of it. All the vitamin C in this lemon is extracted and dissolved in water to make 100 cm cube of solution L. Then from solution L, we then took out a quarter of it, 25 cm cube. And we titrated it against iodine of this known concentration, right? The stoichiometry of the reaction is 1:1. Okay, important information. All right, then they say exactly. So we are given the titer volume here. This is the volume that was required of iodine of this concentration to neutralize the vitamin C in 25 cm cube. Remember, only 25 of the 100. Calculate the amount in moles that were added in the titration. So moles is equal to concentration times volume, which is equal to concentration is 5 times 10 to the minus 3. Multiply that by 36.65 divided by 1,000. Remember to divide here by 1,000. Okay, so that means we have 5 exponent -3, sorry, equal to, multiply that by 0.03665. Am I right? Yeah. Okay, 1.8325 times 10, 1.8325. I want to write it here, 1.8325 by 10 to the minus 4, I guess. Was it 10 to the minus 4? Yes. Right. So you can write this to 36. I can see they're working with minimum number of significant figures, 3 here, 3. So we can give our final answer as 36, right? So our 36 will be 1.83 times 10 to the minus 4. Those were the moles. Use your answer to B part 1 to calculate the percentage by mass of vitamin C present in 150 grams of the lemon. Right, so moles of vitamin C, so moles Vit C in 25.0 cm cube will be the same as the ones we calculated above. Why? Because of the stoichiometry. 1:1, isn't it? So 1.8325. So it's equal to 1.8325 times 10 to the minus 4. Please do not use the rounded number here. So then we can say those in 100.0 cm cube will be times 4 this number. So multiply this number by 4. So we say times 4. That gives us 7.33 times 10 to the minus 4. 7.33 by 10 to the minus 4. These are the moles in the 100 cm cube. Right, so we have gone back to the 100 cm cube. Remember, 100 cm cube was made from the tablet itself. Is that a tablet? I'm thinking about paper 2-1, invariant 2-1 yet tablet, whatever. So it was made from the lemon itself, which was 150 grams. Right, so these moles were present in the 150 grams. So we've been asked to calculate what? Calculate the percentage by mass. So we need to convert these moles to mass. So mass of Vit C, mass of Vit C is equal to, mass is equal to what? Number of moles times molecular mass. Molecular mass of vitamin C is 176, it's been given. So multiply the number of moles, so N times 176 here. Okay, N, which is 7.33, I just don't want to write it. 176. So multiply that by the number of moles times 176. That gives me the grams of equal to, that's a long answer. 29,008, 0.129008 grams. Now, they want percentage by mass. So divide this by the total mass, which is 150 grams. Okay, that's the mass of the lemon. So divide this by 150 and then multiply it by 100%. Okay, that will give you. Okay, so this answer divided by 150 equal to times 100 equal to, I get 0.086%. 0.086%. That's what I'm getting. Okay, I hope you understand the procedure here. I hope you understand. Okay, now the progress of the reaction of vitamin C with iodine to produce M is monitored using infrared spectroscopy. Table 5.1 indicates the presence of some absorptions in the infrared spectrum of vitamin C. Complete table 5.1 to predict which of these absorptions, if any, are present in the infrared of compound M. So let's compare compound M and vitamin C. Compound M, let's see the ones that are present here. So 1,500 to 1,680. Which one is that? Okay, that's the C to C double bond. So we are looking for C to C double bond. 2,850 to 2,000 something, that's an alkane. We are looking for alkane. 3,200, we are looking for hydroxy. So double bond, alkane, and hydroxy. That's what we are looking for in M. So does M have alkene, sorry. It doesn't have alkene. Okay, so the first one, not there. Does it have alkane? Yes, the CH bond is there, you know, the CH bond here. So that peak, we'll see it. The CH bond will be observed. The other one was hydroxy. They both have hydroxy, so hydroxy will be observed. So what's not present is the 1,000, the double bond, 1,500. This one, no. This one will be observed because, like I said, that is the alkane, and then the hydroxy will also be observed. Okay, next. Oh, it's the end. Wow. Okay, we're done. All right, guys. So that's it. I will do the other variant. That's variant 2-3. Then we know we have done all the June structured papers. And then I will see if I can do the multiple choice, all of them, and then move on to the practical paper. But again, all the best with your studies. Watch these videos no matter how boring you think they are. Like I said, if you think these videos are boring and you don't watch, then your grades are going to be extremely boring. Okay, watch these videos. It's not for anything. It doesn't give me anything. It's for you. And your joy will give me joy. That's all I get from it. Okay, bye, guys.